Hello everyone, welcome to lecture 4 right, of the course Software Security. In today's course, we will be looking at assembly language, just sort of like a refresher. Right? We won't be going into depth. So, what instruction, the basic instructions to get you started in assembly language, as far as this course is concerned, right? Software security course. Those instructions and the basics of assembly language we will be looking into. So, for those who already know assembly language and have coded, will be sort of like a refresher. For those who are new to assembly language, just follow through these lecture contents. This will be like a sort of a good head start into the assembly language basics. Right. So, a quick recap of what we had done in the previous session was that we looked at basically the various ELF format files, right? As in the various steps for linking. We looked at what is static linking and dynamic linking, and then we looked at how we load a statically linked executable. So basically, my operating system maps the different sections of my binary file, the code section, data section, everything, into a corresponding virtual memory, assigns a process ID, and initiates a process and passes control to the start function. And the static linking, there are disadvantages because the same function will sort of be copied into multiple statically linked executables, and what this results in is it results in memory wastage. So if you just have 16 GB of your physical RAM, there will be sort of multiple copies of the same printf function in each executable, and it will be loaded each time in the main memory as part of a separate process, right? And this will sort of lead to memory wastage. And to alleviate all these problems with respect to static linking, we looked at dynamic linking, where we sort of keep the library as a shared library, and all the executables which want to use printf, they sort of don't copy the whole printf logic into its code section. Instead, they use um, a level of indirection where they sort of make use of a interpreter at runtime, which is which is part of the executable, the interpreter, and this interpreter sort of finds out where the actual logic of printf is present in the physical memory, and this interpreter fills up a table internally. It maintains some information where the executable sort of calls the interpreter, right? And that interpreter finds out where the actual printf function is located and executes it and returns back to the main one or main two executable. And how this shared library actually saves space is the library is just present only once in your physical memory, but the virtual to physical memory mapping, as in the operating system, it will reserve a part of the virtual memory space that is assigned to each process as a shared library, but it will be only one copy of that shared library will be maintained in your physical memory, and there won't be multiple copies. So we went through like a sort of a rough example where just the mappings are present, but only one copy is present in your physical memory. Whereas in static memory, there will be like two copies in your physical memory, and each mapping from one process virtual space and the other process virtual space, it will be mapped separately to your physical memory, and this leads to memory wastage, right? So these are the different types of linking, static and dynamic linking, and the disadvantages and advantages. And finally, we looked at some code snippets and sort of used the tool readelf and object_dump to make more sense behind what does dynamic linking and static link executables look like, right? So this is the contents we covered in yesterday's lecture. So in today's lecture, we will be looking at the assembly instructions, the assembly language basically. Right. So so basically when we take assembly into consideration, right? Assembly language. So, as far as your CPU is concerned, the assembly language is a true programming language. So basically, uh, you write your code in any programming language, like Rust, C, C++, Java, Python. Finally, all these languages have to be converted into assembly language, and which then would be converted into its machine format. And though that assembly language or that mission format, mission instructions, are the ones that are actually fed to the CPU, and the CPU executes those instructions. So as far as the CPU is concerned, the CPU understands only assembly language, right? All other languages should sort of convert or transform into this assembly language. So it's quite important as a security engineer, you should get to know the assembly language basics and internals, right? And if you remember in last week's lecture, I had mentioned this term called ISA. So basically, it is instruction set architecture. So this instruction set architecture, just a quick recap. So it basically means that what are the instructions that my CPU will understand, right? So there will be like an add instruction or uh, like set of instructions, right? Assembly language. So consider it as a language, right? So what all the CPU can understand, those will all be encoded as part of my ISA. And this ISA is sort of like a reference. It acts as a reference to the compiler engineers, reference to the compiler developers, right? And the compiler developers, so basically I mentioned, right, your C, C++, uh, Rust, Python, Java, everything should convert into the assembly language. And basically this assembly language is the the documentation, right? The standard for this assembly is known as the ISA, right? And the compiler engineers, the compiler developers will sort of use the ISA as a reference, and all your compilation pipeline, the assembly phase and everything, whatever we looked into, will sort of try to convert this source code into the assembly language, which is formally represented by this ISA. Okay, and there are multiple ISAs. So, for example, there is ARM ISA, there is x86, and there is MIPS RISC-V, right? So when I tell a processor is x86 processor, or when I tell it's a RISC-V processor, the internal architecture of the processor, as in like it can have different memory size, it can have like an AI accelerator, it can have um, like an extra GPU unit within it. Or the internal workings of the processor can vary, but the instructions that a processor will understand, right? When I feed some instructions, it should sort of, the processor should be, the CPU should be able to understand those instructions and execute, right? So those instructions which a processor can understand is basically denoted by its ISA. It's represented by its ISA. So when we tell it's a RISC-V processor, it's basically a processor which follows this RISC-V ISA. So when we tell it's an x86 processor, it's a processor, the internal design might vary. So i7 and i3, i7 is faster than i3 Intel processor because its internal design and architecture can vary, all those internal specifications. But the ISA, the instructions that it supports will be same. So that's why it's x86 processors, right? So like this, these are sort of the common ISAs that are used around the world. And ARM basically is mainly in mobile processors and all those stuff. Okay, and x86 is the server Intel processors are all x86 ISA. So in as far as this course is concerned, we will be concentrating on x86 ISA specifically, and that too 32-bit architecture, right? And so the instructions as such won't vary much between 32-bit or 64-bit. So we'll look into what this 32-bit and 64-bit actually means, right, when we look at the later slides. But in all the rest of the lecture, we will be using x86 ISA as our reference ISA, and all our exploits and everything we will be working on x86 ISA reference only. Okay, and if you want to say um, transfer this knowledge to ARM ISA or some other processor, right? So you won't say if you want to find any exploits uh, in your Android applications or something, right? And or sometimes there will be like IoT devices, okay? And these IoT devices won't be using x86 or ARM ISA. They will be using sort of like custom ISA, like some processors ISA, or they will be using this MIPS ISA, something like that. So basically, like once you learn to read assembly language, once you get accustomed to say x86 ISA, right, it's just a matter of couple of days or something. Like you just have to look at that corresponding ISA's manual or reference to find out what the ISA instructions are, the instructions that are supported, and what it actually means when compared to x86 ISA, and that's it. You can easily transfer whatever knowledge you have on with with one ISA to another ISA easily, right? So that's not like a big issue. It mainly boils down to how fast you are able to interpret the manual, how fast you are able to interpret the terms that the ISA um, uses. Okay, so this sort of assembly refresher course will be using x86 ISA, but the same will be somewhat similar to the other ISA types also. So later in your career, if you are going into the cyber security career, you won't just be sticking with x86 ISA, but you will be coming across executables which run on different processors supporting all these different ISAs. So at that time, you should be able to look at the assembly of that corresponding executables, understand that ISA reference, and find the exploit and mitigations and all those stuff. So this will be a good training ground, this course. Right. So as far as when you take a particular assembly language or ISA, right, it's just not the instructions. So one part of the assembly language are the instructions, right? What instructions are the CPU can understand, and usually the set of instructions basically, if you take x86 ISA, there will be like hundreds of instructions, but most of these instructions will not be frequently used, or you won't be seeing those frequently used in your real-time code. As in, when we sort of transform this C, all this source code into the corresponding assembly code, right, by the compiler will sort of have some templates, right, when it wants to convert some piece of source code into an assembly code. Okay? So for example, if my C code is having a construct like if a greater than 0, then a plus plus. So if this is the C code, right, it will be sort of like there will be like a template or something where it will automatically, the compiler will use a set of like 5 assembly instructions or something which represents this entire logic. If a greater than 0, a plus plus. And usually the case is the out of the 100 instructions that x86 ISA supports, only few instructions are frequently used by the compiler. And if you look at the object dump of your source code, right, when you use the object dump command and look at the assembly file that is produced, or the -s flag, right, with GCC compiler, the assembly instructions that you see would be sort of yeah, it will be sort of repetitive. The same set of instructions will be used frequently, right, to uh, implement the logic given in your C code. So even though your x86 ISA sort of contains, if you look at the manual, it will contain like more than 200 instructions, I guess. But you need not, but only a subset of those instructions will be used. You need to really understand how it works to get a good knowledge of x86 ISA. And other instructions, it's sort of as and when you come across those instructions, you should refer to the manual and find out what it usually does. So I will. So there are like very good references, online references for x86 ISA, which sort of in detail specifies what each instruction does. So whenever you come across some unknown instruction which you have not seen before, or you have some query, whenever you are looking at an object compile, you can very well refer to these online references and find out what that instruction does. So basically you categorize the instructions that x86 ISA supports, okay? And the first subset is data manipulation instructions. So basically if I want to copy some data, or read or write something, okay, write some data, all these instructions come under the first category called data manipulation instructions. The second instructions are comparison instructions, which are sort of uh, you compare between two values, you do some arithmetic operation, you add, you subtract, you multiply, all those instructions come across the second category. And then there is control flow instructions. So basically, if I have, say, like a if condition or something, right? If a less than 0, I do a plus plus, else a minus minus, something like that, right? So basically I have to check the condition over here, and based on this condition, the next instruction that I should execute, the next instruction will either be this or it will be a minus minus. So basically the control flow constructs, right? If is a control flow, if else is a control flow construct in C. So to encode all this logic, there are like a set of instructions supported by the x86 ISA. And then there are finally system call instructions. So what we mean by system call instructions is, so we looked at the user space, we looked at the operating system, right? The need of the operating system. So whenever we call the printf function, what does it basically do? So if you look at the logic of printf function, so if you basically look at the logic of printf function, um, it's not over here. Right, so it's not clearly evident over here. So okay, leave it. So if you look at the logic of printf function, right? So basically you have to write something to your display device, your STD out or display device, right? That's the printf function does. And writing to a display device is basically I'm going to access a device where you should use the device driver and all that stuff. So the printf logic, what it does, it should go and request my operating system in order to access this display device, right? So the operating system, it requests and accesses the display device. So basically I'm requesting a service, an operating system service, to access the display device and write my message. So how does my printf function, which is present in as a shared library, or which is present in the user space, right? User space, communicate with my operating system. So one question which you should have is, we sort of mentioned that the the entire address space, right, over here, which slide? Yeah. So the entire address space, right? So if you have an executable, you will have the code section in the virtual memory or data and everything. So where does your operating system be part of this virtual memory? Where is it present actually? So the answer is the operating system is present in a separate memory space. It's sort of like not accessible from your process. So when you try to access any operating system code or kernel uh, or any data section, it will sort of immediately the hardware will stop and it will raise an error, right? As far as in x86 processors are concerned, and to access my operating system, you should sort of request my operating system via some uh, predefined entry points. Basically, in your software terminology, you will be using these terms called API, right? So, for example, if I want to communicate with some third-party library, I should be using that API, right? Programming interface. So that API will sort of have like a standard where it expects like the first argument is some variable, second argument is this, and you should call that specific API function to request that uh, functionality. So if I want to do some AI ML linear regression or something, I should call that corresponding API. So similarly, the operating system, if I want to request the services of my operating system, I should sort of change the context, as in my current context is the which is present over here is um, the current context is the user space over here. So the user space virtual memory. Okay. So now if I want to convert it into, if I want to request the operating system, I should sort of change the context to the operating system context, because my user space process, the process cannot directly access my operating system, right? So it should sort of request the hardware to gain entry into the operating system's code and data sections. And how does it request the hardware? It requests via these special instructions called system call instructions. And in x86 there are like a couple of instructions which are specifically with respect to this system call instructions. So basically when I insert those instructions and when my CPU executes it, it sort of if my code is requesting the CPU to uh, allow me to enter into the operating system context and request the operating system to do some logic, do some servicing like displaying to a device or something, right? And return back the result. And this interface with the operating system is usually done via the system call instructions. So basically, I'm calling the system, right? The operating system. So these are like the general category of instructions: the data manipulation, comparison, system call, and control flow. And as far as that's the type of instructions. As far as this so these are the set of instructions. We'll be looking at the instructions in detail. The second important aspect of an assembly language, or the ISA reference, right, is the number of registers it contains. So registers are basically sort of temporary, fast, accessible very fast actually, very fast access, right? And since they are present on chip, they are limited in count, okay, and they are temporary, and they act as like scratch pads, okay. So basically, all these data manipulation instructions, your comparison instructions, and all these things, they will sort of mostly work on the registers, or they will sort of work on the memory, right? So for example, if I take any instruction, say instruction, uh, uh, sorry. So if I take an instruction like add instruction, okay, and if I want to add two numbers a1 and a2, this a1 and a2, they will either be present as part of the registers or they will be present in memory. And the concept of registers is sort of pretty important because they are like temporary and temporary scratch pads. But why are they actually present in the first place, right? So why do we need registers at all? Why can't we just remove registers and just have memory? Doesn't it make our lives easier? The answer is, if I want to access the memory each time, right, it will take uh, plenty of time to access your memory directly. And what this will result in is, it will result in performance degradation. My running time will increase a lot. So the running time increases a lot, and the concept of registers were sort of are there. So in order to uh, use those, like the frequently used data. For example, you have a piece of logic which takes a number, like assigns a equal to 5, does some operation a plus b, and then c equal to 9, and then c equal to a plus b plus c. Something like that, all these operations it does, right? So now all these variables a, b and c, for fast access, they will sort of be mapped to the registers. They will be stored in these registers, and by storing these used information in registers, you sort of improve your uh, performance drastically. So instead of always going and fetching from memory, you sort of use these registers, right? um, and these registers sort of act as scratch pads. They are like limited in size, right? So for example, if you get some idea or something, you just scratch it on a piece of paper or something like that, and later when you go back home or something, you ponder upon that idea later and you properly draft it in your diary or something like that. So basically these registers have that similar kind of analogy where they are used as scratch pads temporarily just for like fast calculation, like a rough sheet or something like that. And once the calculation is over, it's sort of you can overwrite that rough sheet and keep on using it again and again. But for persistent storage and for the actual reference, you should refer to your memory, right? So that's what the registers are all for. They are basically temporary on-chip scratch pads, and they are having very fast access since they are present on the chip itself. Okay. But they are sort of very costly to implement because since they are present on chip, the number of registers that you can place on a chip will dictate how much power the chip will consume, how much efficient your chip is, and all those trade-offs, right? You cannot keep on placing like 50 registers or something. That will increase the processor size and also the manufacturing cost and the energy consumption and all those stuff, right? So that's like a very limited number of registers you can place. And why do we why is the ISA, the number of registers that can be present is usually part of the instruction set architecture. So along with the instructions that the CPU can understand, the ISA will also specify what all registers, number of registers, and the width of the registers. So basically, each register will have a separate bit. So whether it's 64 bit or 32 bit will sort of be specified in the ISA also, and this bit actually is the architecture size. So when I tell it is x86 64-bit ISA, it basically means I am supporting registers of size, each register is of size 64-bit. It can store 8 bytes of data. If it's a 32-bit architecture, then it means the ISA is supporting some number of registers, each storing 4 bytes of data. So that's what I mean by 64-bit or uh, 32-bit architecture. Okay, and so the ISA sort of specifies what the instructions are and what the registers are. Okay, so these are the two main components your ISA will specify: the instructions and registers. So these two information will be present in your ISA manual. So if you look into x86 or ARM or RISC-V ISA manual, the number of registers and the instructions it supports will be present in that ISA manual. And the first task whenever you are exposed to a new ISA is to look at the number of registers it supports, whether it's 64-bit or 32-bit, and the basic instructions it supports. Right? You need not go and look at all the instructions. You just have to look at the basic instructions. That is, look at these category of instructions. How does control flow take place? How does comparison between two values take place? What instruction is used? How does data manipulation take place? And how do you communicate with your operating system? If you understand these four categories of instruction in any ISA, if you come across any new ISA, you are good to go and start working on that ISA fully. Once you get to know these category of instructions and register, right? And coming to the other aspect of the assembly language, so the other aspect of assembly language is memory. So the memory contents is sort of not part of the ISA. Actually, it's not in the ISA reference. It's not something the CPU should basically be worried about, because it will of course allow you to access the memory, but within your memory it is up to the process or the operating system, right? OS or process to specify how the memory is sort of split into. So basically, if you take any process or any code executable, right, you will have some memory attached to it. It will be accessing and reading and writing from the memory, and there will be different types of memory segments. So one is the stack memory segment, and the other is heap segment. So heap is basically whenever you want to do some malloc or some dynamic allocation, everything will be mapped to the heap segment, right? And the stack is basically used for local functions, local function variables, and call frames, call stack information, right? So this call stack we will look into the last part of this lecture, right? So these are the different memory segments. So if you look at one of our yesterday's code example, we sort of looked at the various addresses each variable is stored in memory, right? The address values variable is stored, and we noticed that the local variables, which are all locally declared in a function, they are all stored in the stack, whereas those which were created using malloc, they were stored in the heap segment, right? So your memory region, even though your entire virtual address space, right, is sort of present with your sort of available to you, it is split into different types for efficient management. Okay, So how it's efficiently managed, like why it is split, we will look in the later part of this lecture when we specifically see into the stack part of memory. Right? It's sort of important for us to understand what the stack memory contents look like, specifically the call stack. Okay. And what do we mean by other mapped regions? So we have stack and heap. What do we mean by other mapped regions? So say I have like two processors or two executing P1 and P2 process. So basically one is sort of like let's say it is a database application running in one process, and the other process is some image or say it is running some internet browser or something like that. Right? So if I want the browser to access some database and retrieve some information, so basically there should be sort of some memory sharing should be there. So basically I should be able to pass some memory, some values from process 1 to process 2. So usually in your function call, if I want to pass some variables from one function to another, everything is part of the single process itself. But whereas here I want to pass between processes. So one way how you pass between two processes is you sort of have a memory area within your virtual memory and mark it as a shared memory. So basically the shared memory can be accessed both by process 1 as well as process 2. And these special memory regions, shared memory regions, allow something called as in OS terminology, which is called as IPC. Okay. Basically, that is inter-process communication. So between processes, you communicate. So one way to achieve this is having a shared memory region between two processes, and say my internet browser will write some data into the shared memory region, and the database of process will read that shared memory and see that okay, the browser application is asking for some data. It will retrieve that data, use SQL or something, retrieve that data and write it back into the shared memory, and the browser will later take that value and do the computation or something. So the shared memory and all those stuff correspond to this other mapped regions within your memory segment. Okay. So with this, right, these are like basically the high level components of any assembly instruction. Okay. So when we if you want to understand any assembly language code snippet, right, you have to first look at the instructions it supports, the registers it supports, and what memory segments it references to. The stack, all the heap segment, and all those stuff. Okay. So, any doubts till now? Okay. Good. So, in that case, let's move to these uh, internals of this assembly language. So over here we have a sort of side-by-side comparison of how my main function will look like and the corresponding assembly instructions. So when we look at the assembly instructions, there are a couple of things that we should sort of understand. Okay, before we look at the example, right? So when we look at any assembly instruction, assembly code snippet, there are basically some set of components which we should understand to better read those assembly instructions, these handwritten or like human understandable assembly format. Okay, so whenever you look at an assembly code, there will be instructions. That's the first component. Okay, so those examples are, for example, move instruction like that. Okay, and the second type in the assembly language. So these directives and all those things, these components, these are all not ISA specified. So The ISA specified, the ISA this specifies your instructions and registers and other aspects. Okay, but the extra things is sort of the compiler supports, as in how does it uh, generate a assembly language which it can sort of has all the information to uh, compile it properly. So basically, whenever you use this GCC -s flag, you get an output, say main.s or something like. So main.c. So you get an output main.s, and this will contain assembly language, right? And the components of the assembly language are basically these are the components. One is the instruction, second are called directives, third are called labels, and fourth is comments. Right? Comments is basically your normal comments, human readable comments. Okay, and so basically these are the four different types of components that you will find in an assembly language. The first is the instructions, which are trivial, which is ISA defined. Okay, the second are called as directives. So directives are sort of special information which is encoded. Okay, so directives are sort of encoded to they sort of act as like metadata in some sense, right? These are not directly used by the CPU, not used by CPU in any sense actually, right? But it is used by my linker, the loader, the operating system to find out how I should place my binary file, how I should do the mapping to memory. Okay, so for example, there is a directive called .section.text. So basically, it specifies that all the contents following this specific directive should be placed in a section called .text. Okay, and so these are all sort of directives which sort of like direct your linker, loader, or operating system on the steps it should take to map these segments into memory, how it should be mapped, what does it mean actually. It sort of acts like a metadata. Okay, and then there are labels. The third component is called labels, and labels is sort of like a symbolic name that you uh, give to some values. So for example, in your object dump file, you would have come across this the main function, and it is present like this, right? Hyphen main colon. So basically, this main is a label over here. It acts like a label or a symbol. Okay, and these labels or symbols are sort of uh, these are also sort of like human understandable feature only. So this has nothing to do with your the actual ISA reference, whatever your the CPU wants to execute, right? So these labels directives is sort of to instruct the linker or the operating system how to go about mapping these segments into memory, what each segment means, what this piece of uh, code or data in the binary file means. So basically, in your ELF file, all this sort of in the assembly language snippet, this will be present. Whereas your label is sort of something which, for your own understanding, it's sort of you specify some values and label those values for easier referencing. Okay. So now let's look at the example that we have. So in the left hand side we have a small main function which just prints a string to hello world to the to the display screen, right? The right hand side contains the x86 the x86 64-bit architecture ISA. So first one to notice is the main function, right? So this main function is sort of converted into this piece of snippet code over here. So the entire this two-line main function is converted into this set of assembly instructions. And in this, if you notice number 7 over here, this is a label, and this label basically denotes a symbol called as main, and it denotes the start of the main function. So this acts as a label, and all these, right, are instructions. Move, sub, move. These are all instructions. Okay, and the second aspect is over here. So this main is a label, but where is this entire logic of main present? Where in which part of your binary it is present means it is present over here. So in this label dot 6, right, you basically specify that all the contents below this is part of a section called dot text section. So basically dot text is actually your code section, right? And all the below assembly instructions and all these labels, all these are part of the dot text or code section. That's what this means, dot text. Okay, and so basically when the operating system looks at this file, right, uh, if you remember the slash proc slash maps file, and if you remember, the code section was mapped to some particular address range, say starting from 0x80 till 0x100, and the operating system sort of specifies the permission as r-x, that is, it can be read and executable, but you cannot modify these instructions. So the operating system sort of uses all this information to place this piece of data code, this piece of chunk, the main function, within the code section, map it to that address region and make it executable. Configure the permissions as read and executable. Now if you look at this specific directive, right, this directive specifies it is a whatever is coming after this directive, these are all read-only data sections, RO data section. And if you remember in the previous lectures, we would have mentioned that any string, constant strings that we are using, these are sort of constants and can be read-only. Okay. So all these constant values are placed in a section called .ro data. And for easier referencing this string hello world, right, we have not given this constant any name, we have just directly used it in your printf function. So what the compiler does is it sort of generates a dummy label called .lc0, which is sort of like a dummy label which is auto generated. And this label sort of denotes this particular string called hello world. Okay, and over here this dot string, if you notice, so let me just erase this particular thing. So if you notice dot string over here, okay, so it is mentioned dot string. So basically this is a directive, and what this specifies is I have a constant value called hello world, and it is of type string, that is what this dot string mentions, and it is placed in this section called read only data. Okay, so this is what this example, this 4, 5, 6, 7, all this over here represents. And if you notice line number 8 over here, right, so if you notice it is some instruction is being used, but specifically if you notice this LC0 is being referenced. So basically what I am referencing is I am referencing this constant hello world whenever I am referencing LC0. Okay, and so these are sort of different directives. So we looked at what are this is a directive, this is a label .lc0. These are all instructions, okay, and these the other things are also directives. For example, this is a directive, okay, and this is also a directive. You represent a section name and all those stuff, and all these together, put together, makes your assembly language. Assembly language. So the directives, the labels, instructions, comments, and everything put together forms a proper assembly language code snippet. Okay, and out of these, the instructions are sort of ISA defined, which sort of has a reference manual. The other things it varies with your compiler and all those stuff, and usually it's the same. So this dot text and dot string and all those stuff will be sort of same. It's the terminologies which are pretty common in any assembly language, uh, ISA, x86 or ARM size. So any doubts in this components of assembly language, the different components? Any questions, or should I repeat anything? Okay. So with this knowledge, right, we looked at what are the different components in assembly language, and we also looked at example how these different assembly language components really look like. Okay, like side by side example. Now let's look at the other aspects of this assembly language, the key aspect, which is registers, right? So as I already mentioned, these registers are like fast temporary stores of data and present on the chip. And usually the number of registers that uh, that an ISA that are present on the chip is sort of ISA defined. Your ISA defines it. So why is the ISA defining the number of registers, and why not it be left to each processor? Why? Because the registers are sort of uh, present on the chip, and all your instructions should sort of support the same number of registers. So basically this ISA, right, it sort of forms a compatibility. Okay, so what I mean by compatibility is, say I want to I execute gcc hyphen main.c, I get a a.out file, right? This a.out file, I should be able to run it on an i3 Intel processor as well as an i7 processor. Okay. So this ISA, so if both the processors support the same x86 ISA, and if the a.out is basically transformed into the corresponding assembly language, which is x86 ISA, then it means that this program I can execute either on i3 or i7 without any issues. Okay. And to execute without any issues, so basically my instructions will be accessing the registers to do any computation, right? And since the registers are limited, say there are just 16 registers, and they will be sort of given numbers, okay, like register 1, register 2, right? The number of registers vary, right? And say I have a program a.out which sort of has uh, which sort of using it's sort of using x86 IC, and assume for now that i3 and i7 are having different number of registers. Say it is having 7 registers and i7 is having 14 registers, and now I want to now execute a.out on i3, means it will have instructions accessing only those 7 registers. But now if I want to do execute a.out on i7, so basically like one aspect is it will only access 7 out of these 14 registers, the other 7 will be unused. And also the other case, the opposite case, right? Say I'm accessing, I'm the A.out references 14 registers and it's supporting i7. But now if I want to execute on i3 processor, which suppose just 7 registers now, then we sort of have to recompile the application, change the instructions to access only these 7 registers and not 14 registers. So this sort of confusion is not should not be there, especially when you are supporting the same instructions, but just changing the number of registers requires recompilation. So because of that and all the other stuff, right? So basically your instruction set architecture defines the number of registers and what usually those registers can, basically the number of registers and the size of the registers. So the ISA defines these two things basically apart from the instructions and other data. Okay, and when you take any register, right? So usually there will be like multiple registers, and there are generally two. You can categorize these registers into different into basically like two types. So one set of registers will be called as general purpose registers, and the other are called as special registers. Okay. So general purpose register is you can use it for addition, multiplication, you can use it for memory access. So basically you can use it for any stuff you can access these general purpose registers. You can use it as temporary scratch pads. Special registers have specific meaning, some significance allocated to them. So for example, in your there are special registers called as SIMD registers, SIMD instructions. So for example, if you sort of use AIML instructions, like vector instructions, they will be like specific registers, vector instructions in x86. Okay. So basically, if you want to do some vector operations, I'm not specifically very sure. So, for example, an array of vector is basically array, right? So, like uh, if you want to like uh, how do we put it across? Um, so, let me give a better example. So usually there are some special registers. For example, there is there are like floating point instructions. So basically, floating point instructions are where if I want to add two floating point numbers like 2.5 and 3.5 or something, my x86 software, the ISA specifies some set of registers separately apart from these general registers, right? These special registers will sort of be exclusively used for these floating point instructions. Okay, so these special registers have that special significance, and they are sort of used only with some certain instructions, and those are special registers. General purpose registers are usually like most of your instructions can use it. Okay, and one key aspect, one very important register that you should all know is known as the EIP register. The EIP register, what this means is the instruction pointer. Right? So basically when you want to execute a code snippet, so if I have some snippet like, for now I'm just using the source code syntax itself, right? So say if I have int main a equal to a plus 5, b equal to b plus 5, a equal to a plus b, something like this, and say it currently my this instruction gets executed. Okay, my CPU executes a equal to a plus 5. Now, how does the CPU know which instruction it should execute next? Right? So all these instructions are also stored in memory somewhere. Right? And say this instruction starts at memory address 0x80. This is at 0x82. This is at 0x84. So basically my CPU currently executes instruction present at 0x80 in the virtual memory. Okay, but now how does the CPU know which is the next instruction it should execute? Basically, how do I communicate with the CPU that the instruction that you executed, that you should execute, is present at 0x80, and the next instruction that you should execute is present at 0x82? How do I inform the CPU? So I mentioned the CPU has an ISA, it supports an ISA. It has, it will understand all the instructions which follow this ISA specification, ISA spec. Okay, but how does it sort of know where that instruction is present in memory and when it should execute? What's the next instruction it should execute? So for doing all these things only, there is a special register called EIP register. So this EIP register sort of contains, so at runtime, no, at runtime as part of the hardware, this EIP register will contain the value 0x80 initially. So it will contain if it contains 0x80, it basically means the CPU should look into this register, the instruction pointer, and see that 0x80 is mentioned, and it will execute this instruction which is present at the address 0x80. And next, automatically what the hardware will do is it will add +2, right? It will fetch the next instruction. And so this +2 can be like sort of, for now I'm telling, but internally it depends, right? So the number of bytes it will increase, the +2 or +3, that will vary, but for now +2, right? The automatically the hardware will do +2, and it will change the EIP content registers to 0x82, and this will next inform the CPU that you should execute this instruction b equal to b plus 1, and followed by that similarly it will keep on changing this EIP register and populating it with new values, populating the EIP register and inform the CPU to execute the instruction at EIP address. So if you notice the name of this register also, it's basically instruction pointer. So basically it's a pointer storing the address of the instruction that should be executed. So this EIP register is sort of very important, okay, and it basically dictates your control flow. So what I mean by control flow is, say if I want to execute these three instructions, means EIP should initially be 0x80 and it should be incremented by 2, and by incrementing by 2 it will sort of execute all these instructions in this particular sequence only, 80 followed by 82 and then 84. So this is the most important register as part of your CPU is concerned for basic functionality executing instructions, this EIP register. But a key aspect, the key takeaway is seeing how important the EIP register is. It's equally important that it should be safeguarded, because say I am an attacker, what I can do is I can try to change the EIP register to some other value. So basically the attacker does not want to execute this particular instruction a equal to a plus b. So after 0x82 is executed, the attacker can do, instead of plus 2 he can do plus 5 or minus 5, something like that. And instead of the EIP register having 84, it will have some value like say 86 or something. And what the CPU will do is it will directly go and see what the instruction is present at 0x86 and execute it. But so basically, if the attacker is able to control your EIP register, then it sort of defeats the entire logic of your function, and the attacker now controls the flow of your program. He can basically change the EIP register to suit their requirements and change how the program should execute. Okay, and usually your hardware systems, right? x86 and the way they would have designed the um, design the processor and all those stuff. Okay, usually the EIP register will be read only. Okay, you cannot sort of directly write into the EIP register using specific instructions, but instead you can sort of manipulate the EIP register using other instructions indirectly. Okay, so directly as in, if I want to say store some particular value in EIP using some particular instruction like move instruction that we'll look at later, those cannot be done, whereas the EIP register is sort of can be updated in very limited ways. So one key goal of the attacker is to gain control of this EIP register and change control flow. So basically now instead of uh, going through the application in a proper logic, say the first instruction, second instruction, like that, the attacker can aim for like a denial of service attack or something, where he can randomly change the EIP register, point it to some other instruction and execute it, and the user will receive like garbage data only, right? So it is important that we protect this EIP register uh, from being misused by the attacker. Okay, and in rest of the following lectures, once we enter into the exploits understanding, right, the final goal of any at least one of the goals of any attacker is to gain control of this EIP register and change its values such that the attacker is now in full control of the application. So once he gains control of this special this important register EIP, he can basically dictate the CPU to execute only those instructions that the attacker wants to execute and not the other instructions. Okay. So this is what is a brief overview of the registers, what they actually mean, and the different category of registers, general purpose and special purpose registers, and the importance of having this register called instruction pointer. Okay. So with this, right, let's look at briefly what registers the x86 ISA supports. So any doubts in the way in the registers, specifically the EIP register and the difference between general and special purpose registers?
No doubt, sir.
Okay, thanks. So in that case, we will look at the different registers that x86 ISA supports. Okay, so here it's sort of like a tabular column I have uh, used. So there are around 16 registers that the x86 ISA supports. Okay, and out of these 16 registers, there are like 8 general purpose registers, as in like all are like they can be used for any usage scenario. Okay, so 8 are general purpose, which are R8 to R15, and the remaining registers, they are usually given some context or meaning. Okay, so out of these the remaining 8 registers, right, the key registers that you will be coming across very frequently in your exploits is these two registers, and yeah, mainly these two registers, RSP and RBP. So this is basically the stack pointer and the base pointer. So when we deal with how the call stack is managed, right, how your stack memory is managed, you will be seeing that these two registers would be frequently used to manage the call stack and your stack memory of a process. And these two registers, manipulating and taking control of these two registers is also important for the attacker to craft, to sort of stage a successful exploit. Okay, and the other registers sort of they are given like specific names. Okay, so there is register RAX. So basically, it is register. Uh, so this is R0, this is R1, like that. Okay, register R0, R1, and so basically these registers are on R0 to R7. They will have sort of like synonyms also, and these synonyms are basically this. So register 0, you can call it as RAX register also. Register 1 is RBX. So you can use either names, but starting from register 8 till 15, there are no alternate names. You should just use it, reference it by its number, R8 or R15. Okay. So what these so these are the registers, and when you look at the column names like 64-bit and 32-bit, all these things, so it basically like sort of x86 ISA supports different architectures. It supports 64-bit architecture. Okay, so in initially like in 1970s and all that stuff, like it was initially having like 8-bit architecture. Okay, so for example, those who will study microprocessors and microcontrollers, right, MPMC or those subjects, right, those old x86 processors, they will be using this 8-bit ISA, and followed by that they came up with this ISA called 16-bit architectures, where the registers were of 16-bit size, and then they came up with 32-bit, and now the commonly used version is 64-bit architecture, where every register is of size 64-bit, and for each architecture it uses, right, the register names will vary. So basically, if I'm on a 16-bit architecture, the register names are AX, BX, CX, like that. These will be the register names. So currently we will be using the 32-bit architecture only. So for that you should concentrate on this column alone, right? So this column denotes the list of registers in the 32-bit ISA, x86 ISA. Okay, 32-bit registers. So if I want to reference register 0, I can reference also as EAX. If I want to reference register 1, I can refer it as EBX also. So this is how the registers, these are all the registers, and based on the architecture supported, these registers are some registers have synonym names also. Okay, but one thing to notice is, despite different architectural size, as in the register sizes, the number of registers were constant, at least from this 16 bits, 32 bits, and 64 bits, right? Number of registers were constant. Okay, and so these are the general purpose registers that are present in x86. Now, one important aspect of registers is, if you want to access a register, okay, so say now I am having a 64-bit architecture, right, and I want to access a register RAX. You can directly access the register RAX. So we'll look at specific instructions later, but assume now I am having an instruction which writes some value into this register. So say I have an instruction move RAX, 16. right? So basically what it means is I am storing the value 16 into the entire RAX register. But one cool aspect with x86 ISA is, even though I am on a 64-bit architecture, so even though my register supports 64-bit size, I can access a 32-bit register also. So basically, instead of move RAX, 16, I can do move EAX, 16. So basically EAX is the 32-bit architecture name of the equivalent of this RAX register. So if I execute this instruction on x86 64-bit ISA, since I am having 64-bit size register, but I am executing this instruction move EAX, then what happens is usually this part of the register will be set to 16. Now instead of move EAX, say I am having an instruction, say move AX, 16, right? So what that means is, on the same 64-bit architecture, right, only this part of the register would be set to 16 value. The other contents of this register will be undisturbed. So say it has some value like 1, 2, 3, 4, 5, 6 and then 0 and 0, right? Now if I execute this instruction move AX, 16, it will set this value to 1 and 6, these two slots, okay? And similarly, if I want to set EAX, move EAX, 16 means 0, 0, 16, then it will erase these values and set 0, 0, 16. So x86 ISA sort of allows this concept, pretty cool concept of partial register access, where even if I am having executing on a 64-bit architecture, I can execute programs which were meant to execute on a 8-bit architecture. So basically, I can write a program which was supposed to be using just 8-bit registers, but I can execute it on a 64-bit machine also because of this partial register access. Similarly, I can execute a 32-bit architecture program, okay, on a 64-bit architecture processor. So that's why if you notice in my in the source code all, I'd have used this option called -M32. So basically it means so this is a 64-bit ISA, the Intel processor that I'm using. So if I use Neo over here, so it denotes it's a x86 64-bit ISA. But I use GCC main.c -M32 to specifically denote I want a 32-bit ISA to be followed. So if you notice the object dump, all the registers that it uses will be like EAX, EBX, all of size 32-bit only. But still I am able to execute that on my 64-bit Intel processor because of this partial register access. Okay. So this is sort of important to understand assembly language, specifically x86 ISA, because in many instructions the entire register, 64-bit register, you won't be accessing. You will be accessing a part of the register alone, the first 8 bits or first 2 bytes of the register, like that. And to refer to those first 4 bytes or first 2 bytes, you will be referring to like RAX, EAX, like that you will be referring to that specific register. So if you notice the table over here, right, if you want to access the first lower 32 bits of the register R8, you should refer it to as R8D. If you want to refer to the lower 16 bits of the register of R8, you should refer it as R8W. So this sort of partial access is allowed in x86 processors. And the ISA also has this documentation or specification, and it dictates this specification. So all this is part of your ISA specification. And why the x86 ISA has partial register access is because for compatibility reasons. So Intel has been in the processor industry for more than what uh, 5 decades or so, right? And their initial systems were all running 8-bit architecture, 16-bit architecture. And whenever Intel is upgrading its ISA, whenever it's increasing the register size, right, it doesn't want its old code bases, the old its loyal customers' code base to become obsolete. So it doesn't want to do that. So make better for them to enable easy portability, right? On execute the old code on the new systems also. It allows these partial register access, mainly for compatibility reasons. And this is like one advantage of x86 ISA because it's sort of compatible to these different architectures like 16, 32-bit, 64-bit. But there is a downside in this decision also because now your ISA becomes very confusing. So if you take any instruction later, right, when we look at the instructions in depth, so when we look at the instructions in depth, okay, uh, these sort of complicate the way the instructions are used. So if I want to say, if I want to have a move instruction, if I have a move instruction, I can either do RAX comma 0 or it can either be EAX comma 0 or it can be AX comma 0, like based on this table, right? Based on this table, if you look at the accumulator column, I can either access RAX or EAX or AX, any part of the register I can access and store 0. So what this makes is it sort of complicates my processor design. My processor now has to understand the instruction and know like which part of the register it should copy the value to. So it's sort of like an extra burden to the processor, and my processor should be able to understand all these different varieties of instruction. So this is one disadvantage in the x86 ISA. And later, when you look into the exploits and all those things, right? This partial register access is sort of a bit tricky because this is something where you should refer to the manual, right? So, for example, in the x86 ISA, there is a condition where if I say I have this RAX register which is 64 bytes. So say this each one is for 8 bytes, right? 8 bytes register. So okay, so 8 bytes register, and this part is EAX, and this part is AX. Okay. Now say my RAX register is having this value 1, 2, 3, 4, 5, 6, 7, 8. Okay, this each is 1 byte. So totally 64 bits. Okay. Now say I want to set EAX to 0, and before that I'm setting move AX to 5. Okay. So when I execute this instruction in x86 ISA, it will remove this. Let it be like 55 or something, right? So this is the first byte and second byte. So basically what it will do is it will set this value to 5 and 5 when I execute this instruction. Good enough. This is partial register access, works properly. But now when I try to access move AX comma 0, instead of 0 let it be move AX comma 4 4 4 4, something like this, right? 4 4 4 4. So now what it does is this instruction, it will erase these contents, all these contents, and set the value of this EAX subset in this RAX register to 444, and also it will erase all these things and zero out. all these contents also. So in the previous case, when I am setting AX to 55, it was only this part was only changed and the other part was not affected. This part was not affected, right? But when I execute this instruction, the other part is sort of zeroed out, the remaining part. So these are all like sort of intricacies involved as part of your x86 ISA. And when you look at the binary code and when you are trying to understand the logic, right, these sort of things will come in handy when you know these intricacies. These will come in handy because you might be trying to uh, track a value which is stored in a register. But say there is some value initially, it's 1, 2, 3, 4, 5, 6, 7, 8, and you are storing some value in EAX register, means the other part of the register, the unused part, the higher 4 bytes will be zeroed out automatically when I execute the instruction. But if you don't know that aspect, you would still be retaining 1, 2, 3, 4, and all your computation will go wrong when you do mentally in your mind. So you should know all these different intricacies to better understand your assembly code. So as part of this partial register access is concerned and this course is concerned, this is one key aspect that you should remember. That is, when you access EAX alone, the upper 4 bytes would be zeroed out, whereas when you access AX register and all the other subsets, the upper 4 bytes would be sort of undisturbed. Okay, so this is what is partial register access. And with this, right, we sort of now we should look into different instructions that are available on x86. So we will look at the instructions that are available on x86 in the next lecture. We'll take some time to uh, go through these instructions in detail. So any doubts till now? So we looked at what the assembly language is, what are the different components in an assembly language basically, the different components, what are the registers, what are the general purpose registers, and what are partial register access, right? And we also looked at a side-by-side example of assembly language compared to its source code, and we also looked at what it means by an assembly language, what does the ISA actually define, and all those aspects. So um, you might be wondering like when will we actually enter into the software exploits and all these things, right? So the reason why I'm going a bit slow on the fundamentals is these are pretty critical, right? So if I speed it up in this area, and I will be sort of uh, you won't fully appreciate these software exploits if we speed up and just glance through all these fundamentals. So it is important that we ensure that we are all on the same page as far as the fundamentals are concerned, specifically the assembly instructions, how the registers are used, this partial register access and all these things, because all these put together, right, understanding makes you build up a complete picture as far as your exploit is concerned, the software exploit. So all these things will sort of come in handy when you want to find an exploit or find a vulnerability. And this sort of critical, this fundamental. Okay. Any doubts in today's lecture? Okay. If not, then we can wrap up the session. I will share the recording and the slides uh, on the GitHub repo and the Google Drive, right? So in that case, let's wrap up the session if you don't have any queries. Thank you everyone. Have a good weekend. Thanks for attending the session.
Sir, thank you so much, sir.
Thanks very much. Thanks, Alpi.